This is my third video on Pollard's method for factorization. So in the first video, I have discussed the standard version where I want to factor an integer. So let us take n is an integer. This is what we want to factor. So for this, we'll apply the basics of Fermat's theorem and we choose a base b. And this integer n generally that we factor is an odd integer. So we can choose a base as even integer such that the GCD of b and n this is equal to 1. Then we take b raised to power b factorial minus 1 comma n. And if this turn out to be a non-trivial factor, then definitely this is a non-trivial factor of n. So this way the method work. You can see in my previous video. In video 2, I've talked about the method when this is not a non-trivial factor. So what will happen when b raised to power b factorial minus 1 comma n, this leads to a trivial factor n. So whenever this leads to a trivial factor n, we reach to this condition that b to the power b factorial, this is congruent to 1 mod n. Because the so if the GCD, so this is the notation I'm writing actually for the GCD. So if the GCD is n, this means n divide b to the power b factorial minus 1. So this congruence will hold. And here I have applied the factoring pseudo prime algorithm. So this also I have done earlier. Now here in this video, we are doing another extension to this method. And we are considering now from the field of integers modulo n. So towards this, first step is choose an easily evaluated map from z by nz, that is field of integers modulo n. So we may choose this as something like x square plus 1. So this is just I'm considering for example. We should consider a non-linear map, not a linear map, because non-linear map will give us pseudo-random numbers. So basically this is based on pseudo-random numbers. We want to generate some random numbers. Again from this is an iterative test. So now let's see what is the procedure. So once we fix this map, which is f of x, and we fix a seed value, which is x, that is equal to x naught. So we may take, say for example, x could be 1 or 2 or any random number. So this is again, we start from a random number and then we start doing the iterative or the successive iterative for the map f. So f x1, this is equal to f of x naught. And then we apply x2. So this is with respect to this map, the successive iterations. So we'll write here successive iterations. So x1 is the another random number that we got from f of x naught. Then x2 is another random number that we get it from f of x1, or we may say f of x naught. And then x3, this is another random number that is f of x2. And we continue this process. So here in this continuing process, we then compare the GCD of xj minus xk for two different indices j and k. And if this is a proper divisor, so this will give us a proper divisor of n. If, so here I will write, if this is a non-trivial factor, if this is a non-trivial factor of n. So this is very much same. Trivial factors of n are 1 and n itself. If this will give me a non-trivial factor, then definitely this will give me a factor of n. Let's apply this in a question. So in this example, I want to factor 91 using the map f of x equal to x square plus 1, and here the seed is also given. So with this seed, we can calculate the other value x1, which is 2, and then we calculate x2, this is 5, and x3, this is equal to 26, and so on. And we know that how I have calculated x1 is f of x naught. So we know the map and we know the initial value. So when I substitute f of x naught, I will get 2. x2 is same as f of x1, and then x3 is same as f of x2. And then we calculate the GCD of xj, xk minus xj, any two different index with respect to n. If this is a non-trivial, we will conclude that we got a factor. Now let's try looking for the GCDs. GCD of x2 minus x1 with respect to n. Let's take the values. GCD x2 is 5 and minus 2. 5 minus 2 with 91. So this is 3 and the 91, the GCD is 1, which is a trivial. So we can say this is trivial. Let's investigate further. GCD of x3 with x2 and n. So in this case, we will see that the GCD of 26 minus 5 and then with 91, this will come out as GCD of 21 and 91. And we find the GCD is 7. So 7, this is a non-trivial GCD. This is neither one. Trivial GCD means either it could be 1 or the number n itself. So these were the trivial options. Now we have excluded this trivial option. So this will give me that 7 is a factor. So we will conclude 7 is a factor of 91. Now in this example, we want to factor the integer 4087 using the polynomial f of x equal to this and the seed x naught equal to 2. So we calculate x1 which is equal to f of 2 and we know that this will come out 7. So simply substituting this value as f of x naught. So this is the x1 I've used and I've get this as 7. So we can calculate now the GCD of x1 minus x naught comma n. That will give me the GCD of 7 minus 2 with 4087 which is equal to 1. Then we calculate x2. x2 will be f of 7. So here I've used the previous seed f of x1. So here then I calculate GCD of 57 minus 7. So f7 is 57. And then 4087. I find this GCD is also 1. Then we continue the process. x3 which is f of 57. This is equal to 3307 and then we calculate GCD of x3 minus x1 and then we calculate n and then we calculate GCD of 3307 minus 7 with 4087. This is also equal to 1. So we need to actually check lot many GCDs here. And similarly, we continue the process. We find x4. This is f of 3307, the previous x3. This will come out to be 2745. And as soon as we start getting the integers which are larger, we should start considering this with respect to the modulo integer 4087. This is very much same as I've done in my earlier video. So and then x5, which is as we expect that now the integers will give us a larger quantity. So try finding them with respect to mod 4087 and write a reduced integer. So here we look for the GCD of x4 minus x3 with n. We find that this is also 1. In fact, we check all possible pairs in such combination. Like we should also check GCD of x4 with x2 and n equal to 1. But there are few strong results which at this moment I am not discussing, which can even give certain condition that if the smaller index, like for here we have the difference between 4 and 2, that is 2, that we have already seen that this index 3 and 2 3 and 1, their difference is also 2 and this GCD is coming as 1. So those indexes difference can be avoided and we do not need to check now the index of x4 with 2 and then x3 with x2 and so on. So you can see that I have skipped some of these. Now we continue with like this x6. So x6 comes out to be f of 1343 and we see that this is 2626 mod 4087 and so again we find the GCD of 4 and 3 that we have already calculated here the index. So I can just try 6 4 minus 3, that is 1. So then I can try x6 with x3 and this GCD is also 1 in addition with the other integers. Finally, we find x7 which is f of 2626 which is congruent to 3734 mod 4087 and we see here that the GCD of x7 minus x3 and n which is equal to GCD of 3734. This is the value 3734 minus, that is x7 minus x3. So I have to take any combination. So x3 is this one, that is 3307 and then we got 4087. This is equal to 61. If I had tried x7 minus x6, x7 minus x5, x7 minus x4, I will find that their GCD is 1. So this is the one step that I've said that we can even improve on to this process. But at this moment, we just can see that if we just find the relative GCD corresponding to these one, and if we find a non-trivial GCD like 61 is a non-trivial, so here we obtain 4087. We got a factorization for this, that is 61 into 67. So this is how we can factor, and this generalizes the concept of the Pollard's method. So we started simply factoring the integers with the previous concept. Here now I am involving a non-linear polynomial. Linear polynomials are not used here, and I start from a seed. The purpose of the seed and the polynomial is to generate certain more random numbers, and then we apply a similar conditions that I've done in my earlier video. There we have used this concept of base to the power b factorial minus 1, their GCD with n should be a non-trivial factor. So this is very much same as this. We have not done a slight proof conceptual, but we can see how this works in the examples.